turn these recordings on. Right, okay. Right, so onwards to the implementation of IRK methods. Right, so we dealt with the order of a method, we dealt with the derivation, so now on to implementation. Now the main sort of disadvantage of IRK methods over the explicit ERK methods is they're slightly harder or slightly more complicated to actually implement. So that's what we're going to be looking at now. Right, so just to remind ourselves, this is the general form of any Runge-Kutta method, not just implicit. This is the form. Now what we'll have is our k values to calculate our the stage values k1, k2, etc. This will be an implicit relationship. So what will happen is if we try and calculate k1, there'll be some k1 appearing on the right hand side. So it's not as straightforward as an explicit relationship. So there's a couple of things we do. The first is this second argument to our function. Remember, we're solving y dash equals f of ty. So f is our ODE function. Now the second argument, the y argument, okay, we're going to say let big Y I equals this part here. Okay, in doing so, that means we can rewrite this equation. So instead of ki, we have our function tn plus ci h yi. Okay, so remember this will be a summation, so there'll be a few of these. Okay, and our y values, big Y values, will be yn plus h. And this kj here, we're going to replace again with the same ODE function. So what this actually has done is it's simplified a little bit. It may not seem like it's simplified, but it has. So if we take equation 3.6 and expand it out, okay, so for any one of our stage values, we take the current solution plus h times this sum. Okay, so we've got lots of function evaluations here. But this is still an implicit equation. So let's say if I was 1, we still got 1 on the right hand side. Okay, so we're going to have to solve this somehow. One method for solving it, which is the simplest method, is going to be called the Jacobi method. And we'll be revisiting the Jacobi method when we look at linear algebra. What we do is we have initial guess values. So we guess what y1, y2 and up to ys are. So we guess what they are, and then we improve the guess values by calculating this. Okay, so if y in superscript k denotes the current guess value, the y superscript k plus 1 denotes the improved guess value. Okay, so we can rewrite this equation as this. So the only change is we've got some superscripts here. Okay, so current guess values and improved guess values. And we iterate equation 3.7. So this is for each stage. So depending on how many stages we have, if we had 2 stages, we'd have y1 and y2. So we iterate this and we're constantly improving. So every iteration we'll get closer and closer to the actual value of yi. We can't go forever. And we wouldn't want to go forever because we've got to move on. We've got other stuff to do. So we stop when the difference between our new estimate and our current estimate, the difference between them is less than some small number tol. And tol is short for tolerance. Okay, we'd actually take the worst case scenario. So if we've got several stages, we take the difference, we use the worst difference between them, so the largest difference. Now that value of tol is some small number, 10 to the minus 4 or 10 to the minus 6 is typical. MATLAB actually uses 10 to the minus 6 by default. Okay, so that's what we do. Quick note here though, Jacobi method is actually computationally inefficient compared to other methods. In practice, we use Newton's method, which is, you may know as Newton's Raphson method. That does require calculation of a Jacobian matrix, which requires some partial derivatives and a solution to a linear system of equations, and it's kind of it's slightly more in depth, so it's outside the scope of this unit. So for our purposes, we're going to be using the Jacobi method. Okay, let's have a look at an example. So here I've got an IRK method. I haven't told you which one it is. I haven't told you the order, but you can, it's one of the popular methods. And I'm going to solve this example. You may recognize this. This was the example that we used for last week for the Euler method and the explicit Runge-Kutta methods. So it's the same IVP as before. And I'm going to use a step length of 0.5. Okay, so initially our T0 is 0 and our Y0 is 1. And we need to iterate this equation for both big Y1 and big Y2 until we reach convergence. Okay, so there's lots of values put in here. I deliberately haven't done this as a works example because we'd be you would just be watching me sort of write down all of these, but I'll explain what these are. Okay, so here we have our current value yn plus h times a11, which is a 1/4, times our function. So it's actually T0 plus C1H, but here we have C1 is 0 and Y1, which is our first guess value. Now I'm going to use, I tend to start my guess values of 1 and 1. It doesn't matter as long as they're kind of non-zero. It doesn't matter what your guess values are. The closer your initial guess values are to the actual values for Y1 and Y2, the better, but more often than not, we've got no way of knowing what they are. So 1 and 1, that serves a purpose. Okay, and then our A12 is minus 1/4, so we have minus 1/4 times F T0 plus C2H, so that's where your 2/3 is, and Y2. So we've substituted the values, do the sums. So we're using an H of 0.5. Okay, we get 0.9866, which is actually not that far away from our initial guess value. And do the same for the second one. So again, we've got yn plus h. Now A21, this number here is 1/4. Okay, and we've got the same function, plus A22, which is 5/12, plus the same function again. Okay, again, if we substitute in the values, we get 1.0223. Okay, so 0.9866 is not really close to 1. So the difference between our two values of y1 is, still relatively speaking quite large, and same with y2. So 1.0223 in our old one value of y2 was 1. So we're going to iterate again. Right, so the same thing this time. If you notice here, our values of y1 and y2, we're using our newer estimates. So the only changes is here. Okay, so we're using our newer estimates, and you can see here we have some new estimates of y1 and y2. They're actually not that far away. So 0.9863, and our old estimate is 0.9866. So they agree to 2 decimal places, and similar with y2. Okay, so we're going to go again. Okay, so the third iteration, again, the only thing which has changed is our value for big Y1 and big Y2. We plug in those values again, we get 0.9863 and 1.0228. So these now agree to 4 decimal places for both of them. Okay, so I'm going to say, all right, we're going to stop there. If I wanted it more accurate, Y1 and Y2, I'd continue to iterate. So these agree to 4 decimal places. That's okay. All right. If I just going to scroll back up. Okay. So now I've got big Y1 and big Y2. I now use equation 3.5. So I know what big Y1 and big Y2 is to calculate yn plus 1. Right. So scroll back down. So I have yn plus h, and this time I've got b1 and b2. So b1 is 1/4. And B2 is 3/4, so that's from the butcher tableau there. Okay, so we have 1/4 times our function, so f of tn plus c1h. Remember, c1 was 0, so that's f of t0 and y1, which is 0.9863. And 3/4 f of tn plus c2h, or c2 was 2/3, h was 0.5, and our value for y2 was 1.0228. and that gives me the solution for y1. So that's just for one step of an implicit wrong getter method. For every step, I'm still going to have to iterate to find y1 and y2. And as you can imagine, that's a lot of work. That's a lot of calculations. So we're going to be writing a program now to actually do the same calculations, but this time using a program. So I'm going to show you how that's done right now. Okay, so this is going to be very similar to the programs which we've already encountered last week, but I'll just start afresh. So always clear your memory, and we're going to define the ODE function, and our ODE function was f of t y. So f equals at ty means t and y are going to be my inputs, and that was the same one from before, times y. Okay, so that was the one we were using. So that's just to remind ourselves, that's this function here. T span is 0 to 5 and y0 is 1. Okay, so I could define the IVP parameters. So we had T span was 0 to 5, y0 is 1, and I'm going to use a step length of 0.5. We're also given the exact solution, so why not put the exact solution in? So define exact solution. Okay, so that's just going to be a function of t, and that's is equal to exponent of t minus sine t times cos t all over 2. Okay, so that's our, we know what the exact solution is. What you should always bear in mind is it's rare, but we ever know what an exact solution is for an ODE. If we did, we wouldn't need numerical methods. Okay, so now what we're going to do is I'm going to invoke the IRK method to solve this IBP. And the way we proceed is, the first thing we need is to know how many steps we're going to take. So the number of steps is equal to the floor, so floor is rounding down to the integer below, of t span 2, which in this case is the upper bound of the domain, minus the lower bound of the domain, and that's over h. So here we've got a range of 5, h is 0.5, so we're going to have 10 steps, but you know, if you had a smaller value of h, you'd want to know how many steps. Okay, so I'm going to initialize my first value for t is going to be t0, which is t span 1, and I'm going to initialize my first value of the array y is going to be y0. Okay, so now we loop for our steps. So we can say for n is 1 to the number of steps. And the first thing I need to do is use Jacobi method to calculate y1 and y2. Okay, so what we're going to do is we're going to write the program or use MATLAB to iterate all of these. Okay, so to start with, I need a guess value. I need some guess value, so I'm going to put both y1 and y2 into the same array just for ease of use, and I'm going to use 1 and 1 as my starting guess values. So that's y1, that's y2. Okay, what I can do now is, if I'm going to loop, I could use a while loop here, but I'm going to use a for loop because it can be a bit neater. So k are my iteration counters. So I'm going to say I'm going to use a maximum of 100 iterations. Now, hopefully, well, it shouldn't really take more than 100 iterations to solve for y. Okay, if it does, it means you've probably got a mistake somewhere. So what we then do is calculate the stage values. So calculate all the new estimates of y1 and y2. Okay, so I'm going to call it y new 1. So this is going to be my yk plus 1. Okay, so we're going to be following this type of thing. Okay, so for this particular implicit Runge Kutta method, we had our current solution plus our step length, and A11 was 1/4. That's times by our function Tn. Now it was plus C1H, but in this case C1 was 0, so that's there, and the second argument is going to be Y1. So just going to show you that that is essentially this this one here. Okay, so then I'm going to subtract 1/4 times my function Tn plus 2/3 H Y2. F of Tn plus 2/3 times H, and Y2 is going to be my second. So just checking my brackets. So that's calculating the first estimate of Y. Now calculate the second one. So it's quite similar in many ways, but this time instead of A11, I've got A21, which is 1/4, just so happens. I'm just going to check that. Is that correct? Yeah, and we've got plus 5/12 says A22. So I've got 1/4 f of Tn plus C1H, which is C10. So that's the same as before. And then I'm going to add to that 5/12 times f of Tn plus 2/3 times H Y2. Just checking my brackets. Okay, so that's calculating my updated estimates of Y1 and Y2. We've got to check for whether we've converged. So we need a check for convergence, and I'm going to use a if statement here. So I'm going to say if the maximum absolute value of Y new minus Y, if that's less than some small number, I'm going to use 10 to the minus 6, which tends to be a sort of standard MATLAB default. Okay, so abs, we need abs because it could be negatives or positives, so just to remove the sign, and we need the max to actually take the worst case scenario. So for example, Y1 may have converged, but Y2 hasn't, so we need to take the worst case scenario. If that's the case, we're simply going to break. Now what break does is that exits the current for loop you're in. So we're in the K loop, and so if we reach this break command, it will exit the K loop and we can continue. What we also need to do is before we actually need to update Y new for the next iteration. So if we update Y new, so we simply set Y new equals to Y. If we didn't do that, this would never break and it would be an infinite loop. It's actually really common to accidentally program an infinite loop when you're dealing with convergence. So remember, the Control C sort of breaks out of any infinite loop. Okay, so all of that effort, that's the Jacobi method for calculating Y1 and Y2. So then we calculate the solution at the next step. So this is your actual Runge Kutta part. So it's Yn plus H, and I've got to remind myself what the B values were for this method. So I'm going to scroll all the way up to the butcher tableau. So it's 1/4 and 3/4. Okay. So here we have 1/4 times our function again. I'm just going to copy from here because it's the same one. And plus 3/4 times a function from up here. As you can see, we're programming a lot of it. We've done it before, so we can simply copy and paste. Okay, so by the way, when we break from this, because Y new and Y are so close together, it's okay to use Y1 and Y2. We don't have to use Y new. Okay, update T as well. So T is Tn plus H, and that's our program. So what I'm going to do is run that to see if it actually works. I notice I have some error here, so let's see what that is. Okay, oh yeah, I've got an erroneous equal sign, so let's get rid of that. See if that works. Okay, believe it has worked. It hasn't outputted anything. So I'm going to output a solution table, and I want my solution table to be formatted. So I'm going to use a little trick which we use in live scripts, and I'm going to have a variable called table, which is going to be full of character strings. Now, sprintf, this is similar to fprintf, where fprintf actually outputs something. sprintf just gives us what's called a character string. So I'll show you an example. So let's say I wanted some column headings for my table. Exact. Okay, and \n gives me a new line, and I'm going to have some horizontal thing there. So if I output that, or if I run that, it takes a bit of a while. Okay, so this is what my table currently looks like. Okay, and then what I can actually do is use fprintf on my variable table to actually output it properly. Okay, you can see there. Right, so now what I'm going to do is I'm going to loop through all of my values of t, and for each value of t I'm going to add to this table character string. So I'm going to have a for loop, and I'm going to for I equals 1 to however long my t array is. So, you know, length t, if t is 10 elements, length t would be 10. And what I'm going to do is I'm going to append another sprintf command to table. Now, sprintf allows for formatted output, and so I want a value of t, which I'm going to output to say 2 decimal places. So %3.2f means I've got a floating point number. That's what the f means, i.e. a decimal. It's going to take 3 character spaces, and it's going to have 2. It's going to be outputted to 2 decimal places. Okay, so and then I'm going to have my my IRK solution. So that's going to be f.4 7.4f. So this is going to be outputted to 4 decimal places, and I'm going to have my exact solution, because we know that we define the exact value up here. Okay, and I need a carriage return, so I use a \n. Okay, so this first number here we're outputting t, let's say ti. Second number we're outputting yi, because that's our the IRK method solution, and the third one we're going to say exact ti. Okay, so that will calculate it for the exact. Okay, so if I run that, let's see what goes on. Oh, we've got an error here. What's happening? We've got a wrong number of brackets by the looks of it. I'm just trying to work out what's going on here. We've got a comma. So %3.2%, 7.4f, %t. Didn't have a comma after that, so I should have had a comma there. Okay, so that's gone away and thought about it, and it's outputted this table. Okay, so from this table, I'm seeing, the first thing I'm noticing is the solution is actually quite far away from the exact solution. So I might have a bug or something, an error in this code up here. So I'm just going to double check all of this. I mean, it can happen. So I'm just double checking that I got all this correct. Okay, and also double checking I have all of this correct. Okay, so +5 have I got a erroneous? Don't know whether that would have made any difference. Let's check. I had one too many brackets. Nope, still going. Just going to see if the initial conditions, sometimes your initial guess values can have an effect on the solution. So nope. Okay. Yeah. Right. So just make sure I've got everything else correct. You know, it can happen. These things. You can have bugs in the program, especially when you're doing it. T zeros. So Irina, you say invoke IRK method T zeros. Yeah. So what you mean by that is we can have these two lines of code here. This actually is a memory issue, so it actually says to MATLAB, I want to store the memory first. So let's see if that's made any difference. I don't think it would have. Yeah, I might have to do the same thing again and bring in the one which I've done before, but I'm checking it against one I've done before and I can't see any difference. It's quite often the case with programming. You might have a bug somewhere. Any other ideas? So check for convergence. One thing we could do is actually output. Let's see what's happening to this convergence. Let's see what this is an exercise in actually bug checking, so it's still useful. So what we've got here is this. Yeah, so I think that's what Irina was talking about. Convergence is not happening, is it? The brackets. So max. So if max is less than that, so what's happening here is it's using the whole 100 iterations to converge when it should normally converge within about 10 iterations. So that's why it's useful to keep track on these. So I have a problem with this code here, so I'm just going to double check this. Yeah, that's okay. So, I really can't see it. Brackets should be after the 6. So in the 6, is there a 6? You mean this? Does that make a difference? No, I don't think that's made a difference. Okay, so what I'm going to do is I'm going to actually copy and paste what I've done before. I can't actually find where the error is, so it must be very similar. Rather than you watch me sort of flounder around trying to find it, there must have been an error in there somewhere. So I'm going to copy and paste one I've done before, which is very similar. And this is the one actually from the printed lecture notes, so you can see. Okay, let's see where. I mean, I can see the bracket after the 6, so that might have had something to do with it. Yeah, okay, so that's closer. Okay, so if we have a look at, if we output how many iterations each Jacobi method took, if I run it, you can see, okay, so the longest it actually took was 11 iterations, so you can see that's kind of different number of iterations each time. I'm not sure what happened with that earlier one. Prize, if you can spot the error in that earlier one, let me know and I'll see if there's a spot prize for you for that one. Okay, right, so back to what we're looking at. Okay, so that's the solution. Okay, you can see it's kind of deviated from the exact solution a bit at the bottom. An easy way to, or we can plot the solution to see what's happening. Okay, so I'm going to plot. Actually, I'm going to plot the exact solution first. So I need I'm going to generate an array of t values. But go from t span 1 to 2, and there's going to be 100 of them. Okay, so t1 is just an array of t values which I'm going to generate the exact solution for. So we're going to have t1 against exact t1 k1. Okay, k lines. K means it's a black line. So I'm going to see if that works before proceeding. Yeah, so Ms. Barr said there was an error in Jacobi. Yeah, I suspected so. Okay, so that's our exact solution. Hold on. So this prevents MATLAB from moving on to another plot. And I'm going to plot our calculated solution. So these commands basically plot it. Each point is going to be a blue dot. Okay, hold off. Okay, should always sort of format the plot. So you can be cute and put LaTeX in. If you know LaTeX and you want to put LaTeX text in, you can. You can see the code from the notes, but for now I'm not going to bother with that. And we have the exact solution in a legend, and we have the IRK solution. Okay, so Stephen, there's a second order. Is it second order? Didn't actually say what order the IRK method was, did I? Nope. Okay, it is a popular IRK method. Can't quite remember what the order is, but you can see here. Oh, it's of order 3. There we go. So this is an IRK method. I think it must be a Radal method of order 3. You can see it closely matches the exact solution, so it's not bad. So we had that problem with the Jacobi iterations. So don't, just because you get numbers coming out, or your code runs and it's no errors in it, and it has is outputting something, don't always assume that it's correct. So here I was able to actually compare it with the exact solution. If you don't have the exact solution, check out how many iterations it's taken. So when I outputted K, it showed that the Jacobi iterations, it wasn't converging at all. So this was never being reached. Okay, so that's one way to check. Okay, that's the implementation of our IRK method. So I'm just going to summarize. Okay, so this week, the stage values of an implicit run-getter method are defined using those implicit equations. So that's why we have to use an iterative solver. IRK methods use fewer stages to achieve the same accuracy than explicit run-getter methods, but on the same time they're slightly more complicated to apply. Derivation of IRK methods varies between different ones. So we choose values of A, B, and C and satisfy those order conditions. We'll see next week about stability, and the IRK methods have better stability properties than ERK methods. IRK methods require an iterative method such as the Jacobi method to calculate stage values. In practice, as I mentioned, we use Newton's method, but that can be quite tricky to apply. So for our purposes, we've used Jacobi method. And also, IRK methods are more computationally expensive when applied to non-stiff methods than ERK methods. Now we'll be talking about the idea of stiffness next week. Okay, so that pretty much concludes what I want to cover in this week. So now you know about ERK methods and you know about IRK methods. You could do much of the assignment which was released, and I spoke about that earlier. There are some exercises for you to check out here. Okay, so I want you to do these but before next week. One thing I wanted to sort of just show you as well, if I go back to my okay, so can you see if I go to Moodle for the ODEs class, if I click on the current week, okay, and scroll down to my part, you can see I've actually put the live scripts, MATLAB live script solutions to last week's exercises are there, so you can check your exercises from those solutions from last week. Oh, and in the I've also uploaded some scans. Okay, I don't know whether you can see that, but that's my scribblings from the additional examples which we went through in the on-campus sessions yesterday. So those of you who couldn't attend the on-campus session, it was only a couple of additional examples, and I've put up those scans there. Okay, you still there? Okay, sorry about the there was that error in the code there. Sorry about that. So does anybody have any questions about what I just spoke about, or also the assignment, or actually anything really to do with the course as well? Has anybody got any burning questions you have? From silence, I guess no. Okay. Has the leader mentioned anything about additional help for this unit as well, in terms of we're trying to schedule or try and find a place in the timetable? Is there anything? Has the leader mentioned anything like that to you? Okay. Right. Okay. I guess not. So essentially, originally I thought that we can have, or there's a gap in my timetable between 4 and 6 this afternoon on a Wednesday afternoon. So if I just check out if I'm free. Yeah. So I'll see if I can find some slots free on a Wednesday afternoon. Yeah. Okay. Thanks, Sophie. So support from next week. Okay. So we'll be able to. Additional support sessions. These are, not compulsory. They're there for you. So yeah, we'll let you know via email about those. Okay, so I think we're finished there. You've had 3.5 hours of sat in front of your screen. So I think you deserve a bit of a break now. So have a good weekend, everyone, and we'll see you next week. Bye.